how to develop 4-bit parallel ladder using 4 full adders using gate level modeling. So first let us create a new quarters project. So it may ask us to close it. So here I'll select the next, and here I create a new folder called PA, and I call this project as PA. And then top level design entity, it's going to be PA here. So now the top level entity is PA, then our lower level modules are going to be full address that we are going to get it done soon. Then I clicked next. It says that does not exist. Would you like to create it? Yes, I want to create it. Then we create an empty project here. And as we know, since we are going to make use of the full adder, so let us make use of the full adder which already defined. So go to the browse to the location and you can select the full adder file. So once you select the full adder file, so it's get added to this project. So then select next. Then we'll change the device to max 10 device. Then we can select next over here. In simulation, we select a model sim Altera and Verilog HDLSD by default. Then click next. Then we can finish our work here. So as we finish this, the parallel adder is the new project that we are starting up. So let us open the full adder module by creating a new HDL file. So in the new HDL file, we are going to develop a parallel adder. Okay, so what are we going to do? It's just going to be a Verilog code for parallel adder, something with a 4-bit adder we are going to develop. So the module name it's going to be module parallel adder, and now the output is going to be of 4-bit. Then it's called 3 down to 0, and I name the output as sum. Then similarly, we'll be having output separately, a output called carry. Then in addition to that, we'll be having our input. So the inputs are of 4-bit size. So 3 down to 0, then I call it as A comma B, both are of 4-bit. Then I'll just declare another input which is of single bit, that is C in. Then we terminate this module definition. Then without fail, I just want to type the end module. So I type it here, and between these two, we are going to define our model definition. But now we ensure that we declare our necessary wires. So we use wires for intermediate carry. So I just name it as C1, C2, and C3 are the wires that we are going to make use. Okay, what is the name of our model? It's called a full adder, which we have already defined. Then we can name it as FA1, the first module. Then first module produces the sum of 0, and similarly the first module produces the carry, that is C1. Then also the input for the first module is going to be A of 0 and B of 0. Then the main input Cin as well. So these are the, as per the port definitions of full adder, we have given the signals over here. Then since I'm going to continue with the same instance, I just change it to name to FA2. Then the FA2 going to produce sum of 1, and the input for so the carry for the SA FA2 will be C2, and the inputs are going to be A1 and B of 1. Now the output of the previous carry will be the input for the FA2. So we define as a C1. Similarly, we get for FA3. FA3 output is going to be sum of 0, 1, 2. Then we'll get the previous, the output of this is going to be the C3 module, C3 carry. Then we get the input for this module A of 2, then B of 2, then the input carry for this is going to be the from previous module, that is C2. So three module we have defined. Next we defined the last module, that is FA4. The FA4 it making use of sum of 3 as an output, and it produces the main carry output, and also now this is going to take the input a comma 3 and the input uh, b of 3 b of 3, and the input carry for this model will be C3. So like this we can define our modules using full address. So now here I save this. So here only I just save it in the name of PA. So I've saved it here in the name of PA here. So once we have done this, next we are going to analyze and elaborate. As we analyze and elaborate, there is no errors. We can go for simulation. Otherwise, we will rectify the errors. So now zero errors. So since already full adder model, everything is included, it's elaborated over here. Then we go for the model simulation. Here in the model simulation, we are going to check the output for parallel ladder. So once again, we go to library, then in the work, now we are going to run the parallel ladder. So as we run the parallel ladder, it makes use of the four bit adder, four full adders. Then we use the objects and it takes away only the necessary signals here, that is sum, carry, and a comma b and c in are the waves that's needed. Excluding the signal, I'm taking the only the waveforms. So then what we do, we take the carry output, sum and carry, we'll take it here. Now here it is going to be a 4-bit value. So I'm just going to force the value here with the like value 1010, and similarly I'm going to force some value for um, B as well, that is 0 1 1 0, something like this. Then I select OK. Then similarly for carry, initially I set my carry to be 0 0. Okay, so now when I run this, I'll be able to see that it's producing an output sum 0 and carry 1. 0 0 is 0, 1 1 is 0, then carry is 1, so 1 1 again 0, then again the 1 1 it's going to be 0, then the carry is 1. Similarly, we can check for the other combinations as well. So if you change the combination like 0 1 0 1, and then we'll be able to see the different output. And now here if you look into it, your output, the carry remains same, whereas the b value is 0 1 1 0. So 1 1 1 0 is 1, then 0 1 is 1, 1 1 is 0, and the carry is 1. So it is 1 over here, and there is no overflowing carry, so the output is going to be 0 over here. So that means it's working perfectly. Then we'll close this waveform and we'll get into the quarters again to check the RTL simulation. So in RTL simulation, we'll be able to see the exact implementation, how it is implemented. So now the system has implemented the parallel adder, 4-bit parallel adder in a way that uses four full adders. Expand it and see, we'll be able to see the full adder that we have implemented earlier. So that gives our parallel adder implementation. Next, what we do, we modify the same code so that we'll be able to get our data flow modeling description by using the continuous assignment statement. So the data flow modeling, we are going to do it now here with the same project. I will just modify this. So here, this already we have defined. So I'm just remove it. So it output and input remains same. There is no change here in the output and input. So we have declared it and we are just going to make use of this. So now here we are just going to write one statement. There's only one statement using assign, and we are going to concatenate the outputs, that is the sum and the carry. So finally what we're going to get is a carry and remaining are going to be sum, that is equal to A plus B plus C in. So this will help us to get the bits added here. So finally, when you get it, then you will be able to see whether it is implemented as a parallel adder or not. Okay. So now let us save this work, and once again we'll run the elaboration. So as we run the elaboration, we will get to know is it throwing any error or not. So it is not throwing any error. Then that means all the signals are correct. So we'll go for RTL simulation. In RTL simulation, we are just going to check the functionality. So now here expanding the work, we'll get the parallel adder. So then we'll simulate it. So then we get objects. So in objects, we get only the necessary signals. Then we add it to the new wave, then the wave, and again arranging my sum and the carry for my convenient. Now I give the input values for A, so I just give 1 1 1 0, and similarly for a B also I'm going to give some other value, that is 1 0 0 1. Then click OK. Then carry I can set it to 0 initially. Then later I want to change, I can change it. So then click OK. Then here when I run this, I'll be able to see that 0 1 carry is 0. So 0 1 it's going to be 1, and 1 0 it's going to be 1, 1 0 it's going to be 1 again, and 0 1 is going to be 1. So it produces 1 triple 1 as an output. So now if you want to change, you can just change only the carry. That also will affect the result. So I'm changing the carry to 1. Then we can click OK over here. Then I run this. Then I will be able to see it's producing 0. How? Because the incoming carry is added. So 1 plus 1 is 0. And the carry is 1, then again 1 and 1 is added here, then 0, then carry is 1, again 0, again 1, again 0, then the overflowing carry, then you'll get the now 0 0 0 as sum, and the carry as 1 over here. Okay, so then now this is uh, parallel ladder is working fine. Now let us run the RTL simulation and check it out. Not RTL simulation, RTL viewer. So RTL viewer, we will run it and check. So when you run the RTL viewer, now we'll be able to see that, and the system has used its own primitive to generate 4-bit adder. So now here you can see that there is one module called add 0 and the other one is called add 1. So which is making use of the main inputs A and B, and it is computing the values using its own implementation and produces the sum and carry from the adder. So that's the system has its own typical implementation and that produces this particular schematic as in the way that it understands. Okay, thank you.